Good morning, everyone. In this video, right, so we will be going through the numericals, the continuation, okay, so which we have seen in the last video or in the last class, okay. So same numericals, okay, few more examples. 250 kilowatt, 440 volt, 600 rpm, 6 pole lap wound DC generator is built with an armature diameter of 73 centimeter and gross core length of 27 centimeter, having 680 armature conductors. Determine for this machine, first one the output coefficient, second one specific loadings, okay, using the above data obtained for this machine, calculate the corresponding design information for a 350 kilowatt 500 725 rpm 6 pole lap wound DC generator. Okay, so now we have to find the values for 250 kilowatt 440 volt 600 rpm generator, okay, lap wound generator, and then with those datas, okay, so we'll have to calculate the designs for 350 kilowatt 500 volt 725 rpm machine, again lap wound DC generator. Okay, right. So first the output coefficient, right? So output coefficient, one equation we have is 0.164 BAVQ into 10 raised to minus 3. Okay, so this equation will not be helpful for us because the specific loading BAV and Q are not available. Okay, so we'll go for the other equation also, which we have C naught is equal to 1 by D square L into P by A. This is from the equation where we used was D square L was 1 by C naught P A by N. From that equation we are using this. Okay, so for power developed, assuming 5% losses, okay, so 0.05 into 250 plus 250, which will give us 262.5 kilowatt. Okay, so now we are going to calculate the value for C naught. Okay, so we have the diameter and the length. Okay, so by using those equation and by substituting for PA, okay, the value which we have got now, okay, so it is 262.5 divided by 73 centi it is, so converting into meters, 10 raised to minus 2 whole square into 27 into 10 raised to minus 2, that is 27 centimeter being converted to meter into 600, that is the N. Okay, so we get it 3.0406 or approximated to 3.041. Okay, so induced EMF, right, we are taking it 450. Okay, so last time also we have seen, right, induced EMF 450, assuming voltage drop of 10 volt. Okay, since it is a lap wound, A is equal to P, which is equal to 6. So total flux P5. Okay, so from the basic equation of E is equal to NP5Z by 60 into A. From that equation we are calculating the P5. Okay, so from that the P5 we get is 0.3970 Weber. Okay, fine, and BF, that is a specific magnetic loading, is equal to P5 by pi dl by basic equation. So we have P5 dl are given. Okay, so when we substitute those values, the value for the BAV, the specific magnetic loading, we get it to be 0.6411 Tesla. Okay, the next we have to find out is the C naught. Okay, so to calculate C naught, right, so we are making the equation B have reg into Q, that is a specific magnetic loading into specific electric loading into 0.164 into 10 raised to minus 3. This equation we have the basic. So from that, right, so we know C naught, the output coefficient, we know the specific magnetic loading, right, so we can find out the value for Q. Okay, so the specific electrical loading is 28,918 ampere conductor per meter. Okay, so now we have both the specific magnetic loading as well as the specific electric loading. Okay, next going to the dimensions for a 350 kilowatt generator. Okay, so they said it is same design data, that is for 250 kilowatt, right? So from that we are taking C naught, okay, 3.04, right? Then again assuming 5% losses, right? So for 350, right, kilowatt, we get 367.5 kilowatt. Okay, and n dash, okay, so here n dash is the speed for 350 kilowatt generator, which is 725 rpm. Okay, so for that, okay, so now d square, okay, and L dash, okay, it is d dash square L dash, okay, which is for the 350 kilowatt generator, the diameter and the length. So it is 1 by C naught PA dash, okay, divided by N dash. So this PA dash and N dash correspond to 350 kilowatt generator. Okay, so it is 1 by 3.04 into 367.5 divided by 725. Okay, therefore it will be, that is d dash square L dash is equal to 0.1667 meter cube. Okay, fine. Next we have the ratio of gross length of armature to pole pitch is same as 250 kilowatt. Okay, as we have same number of poles. Okay, because both we have the number of poles to be 6. So we'll get, right, so L into P, okay, divided by pi d. Okay, so it is 0.27 into 6, okay, divided by pi into 0.73. Okay, so L into P divided by pi d, so 0.7063. Okay, that is what we get. Okay. Next, L dash, okay, is equal to 0.7 into pi d dash by 6. Okay, so that is what we have. So by substituting the values, we get L dash is equal to 0.3665 d dash, or approximately L dash is equal to 0.367 d dash. Okay, so d dash square and into L dash was equal to 0.164 meter cube, and L dash was 0.367 d dash. Okay, so from this equation, right, so 0.367 d dash d cube is equal to 0.164 meter cube. Okay, so d dash, okay, from that we get 0.7645. Okay, and substituting the value in this, okay, that is the L dash, okay, 0.367 of d dash. So this is 0.367 into 0.7645. So we are going to get it as 0.280 meter. Fine. Next, number of armature conductors for 350 kilowatt generator. Okay, so induced EMF 510, right, assuming there is the drop of 10 volt. Okay, number of parallel circuit in armature winding is 6, because A, which is since it's lap winding, so A is equal to P, which is equal to 6. So specific magnetic loading 0.641 Tesla, same as 250 kilowatt generator. Okay, therefore P5 is B av into pi dl. Okay, this is from the basic equation for specific magnetic loading. So from this we'll find out the P5 dash. Okay, so BAV into pi dl, which is as the same as the earlier. Okay, these two values that has been taken here. So P5 dash we get it to be 0.430 Weber, right? And then Z dash, right? So again from basic equation, E dash into 60 A dash divided by P into 5 dash N dash. So 510 into 60 into 6 divided by 0.43 into 725. So we get 588.9 conductors, right, approximated to 590 conductors. Okay. The next numerical, determine the main dimensions, number of poles and the length of air gap of 600 kilowatt 500 volt 900 rpm generator Okay, assume average gap density, okay, 0.6 Weber per meter square, and ampere conductors per meter as 35,000. The ratio of pole arc to pole pitch is 0.75 and the efficiency is 91%. Right? Next one is important, right? So the constraints, okay, the following are the design constraints, that the peripheral speed should not exceed 40 meter per second, frequency of flux reversal should not exceed 50 hertz, and current per brush arm should not exceed 400 ampere, and the armature mmf per pole, okay, should not exceed 7500 ampere, and the mmf required for air gap is 50% of armature mmf, and the gap contraction factor is 1.15. Okay, so these are the given data. So let's see the solution. So C naught is pi square by 60 into BF into Q into 10 raised to minus 3. So we have the value for C naught, okay, equal to 3.4543, approximating it to 3.45, okay, and then PA, okay, so which is equal to, right, 600 divided by 0.91, okay, 600 is the rate, and by the efficiency will give us, so the 659.340 kilowatt, okay, approximated to 660 kilowatt. And then we have the basic equation again, d square L, which is equal to 1 by C naught into PA by N. Okay, so 1 by 3.45 into 660 divided by 900. So it is equal to 0.21256 or approximated to 0.2126 meter cube. Okay. Next you have to select the number of poles. Okay, so here, right, so again as we did in our first problem, we have to choose the P with the constraints, right? So we have seen the advantage of higher number of poles and also of disadvantages of higher number of poles, right? So first we'll have to find out with the basic equation what are the frequency for different poles. That is what it is done. So with this basic equation for a 4-pole machine, right, so we get the frequency of reversal flux to be 30 hertz, and then for 6-pole to be 45 hertz, and for 8 poles it is 60 hertz, right? So from this, right, so the 8-pole is excluded, okay, because it is said that it should not exceed 50 hertz. So we have to choose between 6 and 4. Okay, so next again one more constraint we'll see, so which to be chosen out of 4 poles and 6 pole. So current per brush arm, which is equal to IA, which is equal to 600 into 1000 by 500, so it is 1200 ampere. Okay, right, so current per brush is IA by 2A by P. Okay, so number of poles, and this will be 2, right, therefore, okay, so now for P is equal to 4, okay, so P is equal to 4, so 2 into 1200 divided by 4, we are getting 600 ampere, and for P6, okay, it is 2 into 1200 divided by 6, so which is 400, right? So for the second constraint we had current per brush to not to exceed 400, right? So this is exceeding 600, so this is we had a choice between 4 and 6, okay, as the choice of 8 was eliminated with this constraint of frequency. So now with this constraint, the number of poles for 4 is also rejected. Okay, so with these two, okay, limitations, we are taking P to be 6. Okay, so P is 6 now. Okay, so now we'll go for the main dimension calculations. So again we have L is equal to 0.7 pi d by P. Okay, so it is given, that is the ratio of pole arc to pole pitch, okay, 0.75, okay, into pi into d, okay, into 6. So from this we are getting equation for L in terms of d, okay, 0.393 d, right? So again we are going to make use of this equation, okay, from the basic equation, right? So that is this, right? So here, right? So from that, right, so d cube will be 0.2162 divided by 0.393, right? So d value is 0.81481, right? So approximated to 0.815. Okay, so here we have L, which is 0.393 into D, so 0.393 into 0.815, which gives you 0.3202 meter, or L is approximated to 0.32 meter, right? So next we have the checks. Okay, so about the peripheral speeds, which should not have exceeded 40 meter per second, right? So that is what we have, and that is what is being done here, right? So for that we have basic equation V is equal to pi d n by 60, right? So substituting that, we get a value of 38.405 meter per second, so which is within the limits. Okay, right? And then the armature mmf pole pitch, right? So it is pi, okay, d by p, right? So it is pi, right, into d by 6, right? So that we get, right, 0.4267 meter approximated to 0.27. Okay, so armature mmf per pole ATI is equal to q into tau by 2. So q is, that is the specific electric loading, 35,000 into 0.27, okay, 0.27 divided by 2, which we get 7,472.5. so which is also within the limit, right? So what was given was 7,500. Okay, so next the length of air gap that has to be found out. Okay, so maximum flux density in the gap BG, right? So it is 0.6 divided by 0.75. Okay, so we get it to be 0.8 Weber. Okay, so 0.6 and 0.75, which are the given data, so we get it to be 0.8 Weber per meter square. So mmf required for air gap ATG, which is 8 lakh into BG LG into 1.15, here where it is the value of the contraction factor, which is 1.15, right? So we get, right, so the flux 7,36,000, right, into LG. So air gap per pole, okay, mmf per pole is ATG, which is 0.5 ATA. Okay, right, so we have 0.5 into ATA, right, so which we have calculated. Okay, so 7,472.5, right, so half of that 3,736.25. okay, so now, right, so with this, right, so ATG we have two equations, so 7,36,000 LG is equal to 3,736.25. therefore LG will be, right, 3,736.5 divided by 7,36,000, right, so which is 5.0764 into 10 raised to minus 3 meter, right, or approximated to the value here, right, so approximated to 5.1 mm. A 5 kilowatt 250 volt 4 pole, okay, 1500 rpm shunt generator is designed to have a square pole face. Okay, the loadings are average flux density in the gap is 0.42 Weber per meter square, and the ampere conductors per meter is 15,000. Find the main dimensions of the machine, assuming full load efficiency of 0.87 and the ratio of pole arc to pole pitch to be 0.66. Right? So solution PA by 5 by 0.87, that is efficiency. So we have it 5.747 kilowatt. Okay, so that is the PA. So again by C naught, that is output coefficient, pi square by 60 into BAV into Q, specific magnetic loading into specific electric loading, right? So we have that. So right? So which are given 0.42 and 15,000, right? So we get it to be approximate value of 1.03. Okay, and then d square L, right? 1 by C naught PA by N. So 1 by 1.03 into PA 5.75 by 1500 speed, that is the RPM, right? So you get it to be 3.721, right? Into 10 raised to minus 3 meter cube, approximated to 3.72 into 10 raised to minus 3 meter cube. Okay, and then the equation L is equal to phi psi pi d by p, right? So which is 0.66 into pi into d by 4. Okay, so therefore L is equal to 0.5183 d approximated to 0.518 d. Okay, so by basic, right? So this d square L equation, okay, so 0.518 d cube is equal to 3.72 into 10 raised to minus 3. Okay, right? So from that, right, so this value, so from that the d value is 0.1929 approximated to 0.193 meter, and L is equal to 0.518 d, so 0.518 into 0.193, so L is equal to 0.0999 meter approximated to 0.1 meter. Find the diameter and the length of armature core for a 75 kilowatt 460 volt 14 RPS, that is the revolutions per second, 4-pole DC motor having a full load efficiency of 91%. The product of specific magnetic loading and specific electric loading is related to diameter as follows. Okay, so this is the product. Okay, so we used to see in C naught. Okay, so it is right with respect to the diameter. So for 0.1 meter diameter, the product of the specific loadings are so much. For 0.2 it is 9,300, 0.3 meter 12,700, 0.4 it is 15,500, and for 0.5 it is 18,000, and for 0.6 it is 20,000. Okay, and we have expressed in Weber per meter square and Q in ampere conductor per meter. Okay, take the ratio of pole arc to pole pitch to be 0.7. Okay, and then select the design which gives a square pole face. Okay, right, so this is the solution we have. So power developed by armature. Okay, so PA, right, so P into 1 plus 2 neta divided by 3 neta. Okay, that is the efficiency. So it is 75 into 1 plus 2 into 0.91 divided by 3 into 0.91. Right, so which is 77.472 kilowatt approximated to 77.5 kilowatt. Right, so PA, right, is equal to C naught d square ln. Right, fine. So here, right, so we will go for, right, the small n. Okay, that is what, so small n is nothing but capital N divided by 60. Okay, that is why this is cancelled. So I'm taking the small n, that is the revolutions per second. Okay, so that is this change made here. So we get pi square BAVQ d square L into 14 into 10 raised to minus 3. Okay, so now PA is 138 d square L BAV into Q into 10 raised to minus 3. Okay, therefore L will be equal to PA into 10 raised to 3, this minus 3 up, so 138 into BAV into Q into d square. Okay, so this L is what we are finding out. So it is 77.5 into 10 raised to 3 divided by 138 into BAV into Q d square. Okay, so L is equal to 562. Okay, 562 divided by BAV Q d square, that is the specific magnetic loading into. Okay, so next right? So for different diameters, right? So you can see L is here, okay? This product is given to us. The variation is with the D. So for different D, right? So we'll be finding out the values for L, okay? So that is what. Okay, so from the above equation, we can find the length of various diameters and also the ratio of length to pole pitch. Okay, so that is what we are doing here. So diameter in meters for 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, right? So this BAQ into D square. Okay, so those values will be 52 for 0.1, right? So that is here nothing but, right, the values that is already given, right? So here you can see 52.1 square, so it will be 0.01, so it is 52. Okay, so that is what is done here. 0.1, it is 52. Similarly for 0.2 diameter, right, so it is 372. Okay, then for 0.3 it is 1143, 0.4 it is 2480, 0.5 it is 4500, and 0.6 diameter 7200. Okay, so from this, right, so we are getting this values, this, so we'll be getting the value of L. Okay, so when we have, right, so 562 divided by this 52, okay, so 10.8. then similarly here, right, so 562 divided by this value, that is the 372, 1.51. okay, so for 0.3 it is so much, right, so 0.4 diameter 0.227, so for 0.5 0.125, and 0.6 diameter 0.078. so these are the values L, okay, for the corresponding D. Okay, and from the table, right, so we can know that the length corresponding to 0.1 m, 0.2 m, and 0.3 diameter are too long. Okay, so if you can see here, right, so it is 10.8 meter, 1.51, and 0.49, and approximately 0.5, that is half of a meter. Therefore, right, they are too long. And for 0.6, right, it is too short. Okay, so it is for 0.6, it is 0.078 meter, which is too small, right? So the remaining is, right, so machines with 0.4 and 0.5 diameters, they are having normal designs, right? So now the selection has to be made between 0.4 meter diameter and 0.5 meter diameter machine, right? So we have this. Okay, so this is the diameter, the length that we have got, pole pitch, okay, which is nothing but pi d by p. Okay, pi d by p, we get these values. Then the pole arc b, right, so which is nothing but 0.7 into tau. Okay, 0.7 into tau, and then the ratio of L by B. Okay, we have the L by B. Okay, so we get these values. Okay, so for 0.5, the length is 0.227 meter, the pole pitch is 0.314, pole arc will be 0.7 into this, so it is 0.22, this 0.7 because they have already given the ratio. Okay, so pole arc to pole pitch, what is the ratio they have given? So from that we get 0.22. Okay, L by B, right, so 0.227 by 0.22. Okay, so 1.03. Similarly for 0.5 diameter, the length is 0.125 meter, right, so pi d by p. Okay, so we get 0.471, and then for pole arc 0.7 into the pole pitch, right, so 0.7 into 0.471, so which is 0.33, right, so it is, we get around approximated to 0.33, right, so the L by B is 0.38. Okay, so the design with 0.4 m diameter gives a square pole face. Okay, so how is that decided? Is by this. Okay, so it is almost nearer to 1. Okay, so L by B, so the L and B are the same, they have to be, that is what we are standard for, square pole face. Okay, so since this is giving us nearer to the square, right, so that is why we are taking it to be 0.4 m and L to be 0.227 meter. So for us, these values, that is for 0.4 diameter, the corresponding lengths are selected. Thank you.